So whenever you're ready to launch, I think the rest of us are ready.
Okay, hello everybody. I'm Gordon Rosner, your president, and this is our July meeting. You can see the agenda there, those who are waiting for this to start. We have a member presentation by Sid Friede, and our main presentation is by Felipe MacAuliffe. So we'll jump right in and get going here. And as usual, live long and prosper, everybody. Introductions, as always put this up so that everyone knows that the club, this is the leadership team. The team is still working to keep the club going. And we still have one position open. It's a property administrator. And what that person does is whenever we get a call or a notice that someone wants to donate some equipment, then this person evaluates that equipment, sees if we want to actually accept it, bring it over to our shed, which is by the Greco Observatory, and then keeps track of it because chances are we're either going to redonate it to some educational organization or maybe put it up for auction during one of our yearly auctions when we get back together. So that position is still open. But remember, the most important member of the club is you, everybody here that's up there watching this. You are the important member of this club. Club news are, as I always say, club olds because it's the same old thing. But remember, Greco is open for private star parties. We have not opened it up yet for our normal public viewings, which would be normally on Friday and Saturday evenings. But what Claude is doing is in our website, you can go on Greco and request to get in for a private star party. And generally they're small. It's like a family, like maybe 4, 5, 6 probably at the most people. Some students also come on in, some visitors out of town. And Claude gives them about a 90-minute look at the sky through our Greco Observatory. So that is going on Mondays through Sundays through Thursday. But again, remember, they're still not open to the public yet. Just like all the other EVAC personal contact events still remain canceled. We don't know when we're going to open up yet. We were hoping September or October, but we'll just have to see how things go, especially with changes in this pandemic. But still, remember, there is no in-person events that are happening right now. And this is a standard slide. Remember our member presentations. You'll see a great one coming up by our members. If any of the member wants to give one, let me know and we can work here right on. And then also member articles. So we are accepting newsletter articles. If you get about a page or so on something that you're interested in, something that you went to, about maybe talk about your equipment and your frustrations that you overcame. So anything that would be of interest to astronomers, get a hold of me and we'll get you in on the newsletter. And remember that these monthly meetings are being recorded and a link is provided on the EVAC website. Just go into the website and under events and meetings, then they're listed in there. So, hey everybody, remember the Perseid meteor shower is going on right now. It just started a few days ago. So as you go outside, if you're not watching the rain and the clouds, hopefully they clear up and you'll be able to see the Perseid meteor shower. So they last in through, maybe towards the end of August. Its peak is about the 11th of August. So they're starting now. In fact, I saw one last night through some holes in the clouds. I was looking at Venus and Mars on how close they were together, and I saw one zing on by. So the best time to see them, of course, is after midnight. Then a little history down at the bottom that it's from a dust particle from a comet known as Swift-Tuttle. So that's what we're passing through right now. So our next EVAC meeting Remember, it's going to be Friday, the 20th of August, same time, 7:30 p.m. Main presentation will be by Alan Friedman, minimum to the max. Now, let's see, minimum to the max, what does that mean? Well, he's talking about the sun. The solar cycle is rising, and I think, as I recall, I think it's solar cycle number 25. And I think that's right. So we're climbing out of the time, that 11-year cycle, when the sun is kind of what we'd say sort of dormant, not very many sunspots, not very many flares, prominences going on. But we're climbing out of that, and we're starting to see these things now. So that's what Alan will be talking about, is going from minimum to a solar maximum, and what we can expect to see. So our Vice President, Tom Mozdzen, he will introduce our main president. Oh, I'm sorry. First off, we'll go with Sid. I'm sorry, there's Sid. I skipped a slide over. Sid Friede is our a member who started astrophotography maybe, over a year ago, maybe 2 years ago now, and he has really dived into it. So he's going to give a presentation about demystifying image calibration. So Sid, I will hand it over to you. I can get out. There we go.
All right, are we on?
Yeah, looking good, Sid.
Great. My name's Sid Friede, and tonight I'm going to talk about astrophotography as a journey and not a sprint, specifically talking about calibration files. You know, in the modern era today, you can take a photo with your smartphone with outstanding resolution and clarity, and it's automatically uploaded to the cloud, instantly shared with your friends on the internet. But astrophotography is not quite so easy. I found that out, I think, the hard way as well. You're basically attempting to take a photo where you're literally counting individual photons that may have traveled hundreds of millions of light years to be captured by your camera sensor that's no larger than a postage stamp. And when you think about that, it's a pretty incredible feat, just as that is. And it can take hours of exposure just to get enough data to create one image. As far as myself, a little bit of background. I joined East Valley Astronomy Club last year, attended a few meetings, and then COVID hit. We started remote meetings. I got interested again. I dusted off a scope that I actually bought back when my son was in high school, and basically joined the backyard COVID astronomers. And I developed an interest in trying to take some photos. And I soon realized that my old equipment needed to be updated. So I ordered a new scope in April and got into the front end of the delivery issues that affected our industry. But it finally arrived in September. So I started doing some imaging last November. So I'm pretty much a certified newbie in astrophotography. Before I get started, let me give a disclaimer. The following document is comprised of sometimes incoherent ramblings of a wannabe astrophotographer. The opinions are solely my own, sometimes actually based on fact, but mostly a compilation of pieces of knowledge which may or may not be correct. Experienced astrophotographers may cringe at my process or conclusions, but if so, I ask for your help. I made the journey with the help of various friends, forums, Facebook groups, and YouTubers worldwide. I think I have a process now that kind of pleases me and challenges me, and really isn't that the purpose of a hobby to begin with. I feel like I'm drinking from a fire hose, and I'm excited about continuing my quest for knowledge and competence. Image calibration demystified. It really was, to me, in trying to get my head around that, a mystery. It was very difficult to understand the whole process of calibration files, how they're used, and everything involved in the calibration files. So I really kind of started taking a look, what are kind of the three basic categories of astrophotography? Number one is capture, one of the first C's. And it's the camera, the lenses, the telescope, the mount, the guide camera, the guide scope, the filters, exposure times, all those things that we are required in order to capture data that we can try to process into this glorious astrophoto. On the other end of the process is creation. That's when we finally have data that we can take into PixInsight or Photoshop or whatever our image processing software might be to try to create that photograph that we're trying to capture.
Fred, you're muted.
You hit the mute button somehow.
Am I back?
There you go.
Okay. In the middle of the capture and creation is calibration. In order to take all that data that we've taken all those hours to acquire, we have to be able to process that so we can actually do a creation in our imaging processing software. And really kind of what we're talking about. We're dealing with the good, the bad, and the ugly. When we take a light frame, we have all of that. We've got good stuff and bad stuff and ugly stuff. The good stuff, that's the photons from our target. That's our picture. That's the thing that we want to process and save. The bad stuff, anytime we apply power to our semiconductor sensor, we get bias issues, we get dark current, thermal noise, hot pixels, all sorts of bad things that are inherent in our photo sensor that we want to get rid of in our processing. And the ugly stuff, these are the optical aberrations in our image train. This is the dust that's sitting on our lens or on our filters, the vignetting we see as part of our image train, and other kinds of things that are introduced as a result of the equipment that we have. So when you take a look at a light frame, it includes everything. And I'd like to thank Atom Block Studios. Many of you know Atom Block, are familiar with Atom down at the University of Arizona. And he has access to all those wonderful toys over at Mount Lemmon and creates some just amazing astrophotographs. So if you have a chance or haven't been there, take a look at his website at all the things that he's produced and captured. And again, I'd like to thank him for allowing me to use some of his graphics. He had a very clear representation in talking about calibration files and how they used them, and he was kind enough to let me include those. If you take a look at the histogram of a light frame, most of our data is over in this corner on the dark side. Dark being here and light being over in this corner. When you take a look at the night sky, our eyes pick out the stars and all those images that we're looking at, but in reality, we're basically taking a picture of black. The sky is mostly black, and most of our data lies down at this end of the spectrum. That's the good and the bad, the ugly. The bad part is all the information that's associated with our semiconductor sensor. These are bias currents and dark current issues. The good stuff is in our signal, the good photons, but in this signal also we have photons of our ugly stuff. So what do calibrations do? Basically, what the calibration's purpose is to remove all the bad stuff, removing the unwanted noise from the sensor and removing those optical aberrations from our image chain, the bad stuff and the ugly stuff. So what are they? What do they do? How do you take them? And how do you use them? Calibration frames are basically images or pictures that we use to isolate the noise and those optical aberrations. So what do? They remove those. If we can oscillate those in individual photographs, let's say, we then can subtract them from the image, leaving only the good funds of our target, which we can take to process our photo. So how do you take them? Well, dark frames are separate exposures in total darkness. We're eliminating all photons that may have resulted from our target, and basically we're taking a picture of our sensor noise. Flat frames, they're separate exposures in intense light. We want to intensify the light, so we're emphasizing all those ugly parts of our image train so we can more easily remove them from the photograph. So how do you use them? Well, the cool part about this is that we have some software tools that pretty much do that for you. Once you take them, you basically feed them in, press the magic button, and out pops a calibrated light frame that you can use to process. And I'll talk a little bit more about that later. So you heard terms about light frames, dark frames, flat frames, which we've talked about before, bias frames, sometimes more relate to CCD type sensors. And then we run into something called dark flat frames and flat dark frames. And all this can become very, very confusing. So back to our light frame again. Again, our histogram where all of our good, our bad, and the ugly shows up here. And back again to our photograph or our graphic of our total light frame. The good, the bad, and the ugly. Our semiconductor information and the photons both are from our target and from those optical aberrations. So dark frame, again, we take in total darkness. We cover the scope, put on the lens cap. And I found out also that you pretty much have to make sure that you actually cover the scope and eliminate all possible light from hitting your sensor. Typically, the image trains are not totally dark. That light can encounter those, and you have to make sure that that's totally isolated. Now, dark frame is sensitive as far as time and temperature. We need to take the dark frames at the same time and temperature we take the light frames. This is a histogram of a dark frame, and you can see our data down here is fairly small, and it's in the dark range, certainly, of our histogram. So to take a dark frame, it's again dependent upon the exposure time and also the temperature we're taking that. So typically what we would do, we'll take a number of frames, somewhere between maybe 25 and 50, which include the bias component and the dark current component of our semiconductor sensor. Our software then will integrate them into a single frame we call our master dark. That as a representative of our noise and of our dark current. The flat frame, again, we're trying to get a reasonable interpretation of those optical aberrations. Here we use an intense light source, basically half of our total spectrum. If we remember that histogram, we're somewhere in the middle. And you'll hear things about T-shirt flats and LED panels and a variety of ways of taking those. But we want to take basically a very short duration flat frame from 1 second to 5 seconds at approximately half the total light intensity. That gives us a very clear definition of those optical aberrations. So if we take a little closer look at that. Here's a histogram of what our flat frame looks like. And you can see there's a lot more data there because we're using a very high intensity light source to isolate those aberrations. This is kind of a representative photograph of a light frame. And these little ugly circles are specks of dust. Those are the things we're trying to eliminate. You can see also some vignetting in the corners of our frame and the types of gradients that the flat frames help us to eliminate. This is a stretched version of a flat frame. And you can see here, hopefully it shows up, you can see those circles. Those are specks of dust in our image train, which we now have isolated so we can use this flat frame to take those out of our exposure frame, removing those ugly photons. So to take those, again, we'll take a series of frames. This again is a 1 to 5 second frame at the same temperature that we're taking our light frame. Now, we're also exposing our semiconductor sensor. So we're back and taking a look at some of this bias current and dark current. Well, this dark current is very, very small because our frame is only a second or so. But we still have to eliminate this component. So we take a flat frame or a flat dark or a dark flat, depending on who you talk to. But this frame, again, is taken with the scope completely covered at the same time and the same temperature as our flat frame. So then we subtract this from the flat frame because we don't want to do this twice because we just did that from our dark frame. So now we wind up with a series of flat frames that are only basically the ugly photons. We integrate those again with our software, and we wind up with one master flat frame, which now includes all that ugly part of our image. This is just one method of taking a flat frame, and there are many. This is basically a needlepoint hoop, and these are 4 layers of a white T-shirt. Just got from Target and ripped them up. This is my dew shield. I've got a LED panel sitting on top of that. This happens to be a 5-volt panel. So I just plug that into my powered USB hub. It sits in my tripod, which powers the light panel. And I've experimented with this so that I've got the right combination of numbers of T-shirts and some filtering here that I can take a 1 3/4 second flat frame and get that center point ADU or about half that in light intensity. So it's very easy now to set up. I just come out, throw this together. I can take 25 or 50 flat frames. Again, they're only less than 2 seconds long, so it doesn't take very long at all to take those flat frames or calibration frames. So we've got that raw light frame that includes the good, the bad, and the ugly. We've got the master dark frame now, which is the bad stuff. So now we're left with a frame with good and ugly. And now we take the master flat frame and we take that away from our frame. And now we've only got the good photons. These are the photons we've been looking for. This is our picture. So now we have a series of calibrated light frames that are integrated now into a single master light frame. And this is our image that we're ready to take into our processing software. If we take a quick look at kind of what's going on here, this again is our light frame, the good, the bad, and the ugly. This is our dark frame, picture of what the bad looks like. And here's our flat frame with the ugly stuff. This is an individual exposure stretched by our software. And when you hear the term stretching, we're talking about basically taking this section of our histogram and expanding it all the way across the light spectrum. So now we can kind of see what we've got in a single exposure. You can see now this is M51. You can see the 2 cores of the galaxy. We're starting to see the details of the spiral arms. and we're seeing a sprinkling of the stars in the photograph. This is a dark frame, again, stretched, and now it looks like that it snowed. What's all this? This is hot pixels. And our sensors, however, are not perfect. So sometimes we get pixels that are very hungry for electrons, and they basically saturate and become totally white. Well, it looks like a lot, but this particular sensor I use is 3,000 pixels by 3,000 pixels. So you're looking at 9 million pixels. So even though the hot pixels stand out, there are really very few of them in comparison to the actual pixels that are capturing our image. And our software takes care of taking those out of the picture. Again, this is our flat frame. We saw this before. Our dust motes, our vignetting. We've got some vignetting here in the corner. I got a dark strip across the top. I use an off-axis guider. So the prism actually drops down into the light train to pick up the stars for guiding. And it creates kind of a shadow across the top of the frame. And our flat frames will help eliminate that. So calibration frames, again, a quick look again at our raw light frame, the good, the bad, and the ugly. Our master dark is the bad, we get rid of that. Now we're just left with the good and the ugly. We have our master flat, which gets rid of the ugly. And finally, we wind up with a frame that has only good photons from our target. Now, it sounds complicated, but really the software simplifies that for us. For an example, there's a program called Deep Sky Stacker. The beautiful thing about it that it's free, you just download it. And basically, you load all those files into Deep Sky Stacker, press the go button, and the software takes all those files and produces that master light file we're looking for. Here's a screenshot of Deep Sky Stacker. It calls them picture files. These are our exposures, our light files. Load in our dark files, load in our flat files, load in the dark flat files that we took, and basically press go, and you wind up with a single master light file, which we're going to take off to our imaging processing software and PixInsight or Photoshop or whatever you're using, and then create that photograph that we're trying to get. And again, this is Deep Sky Stacker, great program. Probably everybody who uses or is still using it. Wonderful program, and it's especially free, which makes it even better. Well, now we're talking about, okay, I'm taking maybe 3 or 4 hours of exposure in an evening. I need to have some dark frames. Well, if I take a 300-second exposure or 5 minutes, and I need to take 50 dark frames, 50 times 5, I've got to take 250 minutes of dark frames. That's over 4 hours of dark frames. So now I'm taking 4 hours of light frames and 4 hours of dark frames. I'll never get any sleep. Well, the good thing is that dark frames are a product of our sensor, and our sensor changes very little over time. So once you take a dark frame, it's good for 3 to 6 months, maybe longer. So what I do is every maybe quarter or every 6 months, you can sit down and a couple of nights, take your typical exposure times, maybe it's 1 second or 1 minute, 2 minutes, 3 minutes, 5 minutes, 10 minutes at the temperature you're going to be exposing, and just build a library. And then anytime you do an imaging, you can just refer to that library, pull them in, and your dark files are available. Flat frames are a little more dependent upon your exposures. Again, in Arizona especially, we have a very dusty environment, so you'll find that those little boogers, dust specks will appear, and those dust motes will show up. So you typically take your flat frames relatively often. Sometimes you can take them once per session, or in the case of one I'll show you in a moment, I had 3 imaging sessions over 6 nights. So you take one set of flat frames, which will apply to all those sessions. And if your scope happens to be inside a dome outside, or it's better protected from dust and environment, you can probably use those flat frames longer than that. And again, flat frames are only from 1 to 5 seconds, so it's easy to take them. And the dark flat, it's a dark frame, and it has the same characteristics that our full dark frames of our exposure. So knowing now that I'm taking most of my flats at 1 3/4 seconds, I have a dark flat library that again is in my library. So when I do an exposure calibration, the dark flats and the dark frames are already in my library. Here's an example of a typical imaging session. I did this in June of M51. There are a total of 253 frames to produce 1 master light frame. So I had 133 light frames at 300 seconds. That was about 11 hours. It was over 3 different nights over a period of about a week. 40 dark frames at 300 seconds, same time and the same temperature. And I pulled those from the library. 40 flat frames at 1 3/4 second. And I used one evening to do flat frames. I don't recall whether it was the first or the second or the third night, but they applied to all the images I captured over that week. And then 40 dark frames to calibrate the flat frames. And again, those are in the library. So the only thing I had to do is I took my light frames, I took 1 evening of flat frames, I'm ready to go. So those are integrated into a single master light frame. And it looks something like this. This is a unstretched single light frame of that N51 exposure. And said, well, it's dark, there's nothing there. Well, again, remember, we're taking a picture of basically black, and our data is there. So if our software stretches it, we saw this one before. This is a single image of M51 that was exposed at 300 seconds. So there were 253 exposures were combined and calibrated into a single master light frame. And now we're starting to see some data. We've got some data in the core. We can see our spiral arms. We've got our stars. We've got some nebulosity now that's starting to appear around the M51. So we take that one master light frame now that was generated from 253 exposures. We take it into our Photoshop or PixInsight, and we get this. It's amazing that you can go from this one single master light frame to this type of a frame with all this color and definition and detail. And this was one that really kind of surprised me as well about how well it came out as far as early on in the processing. In fact, I load some of my files up to AstroBin, and ZWO is the manufacturer of the camera that I use, and they browse AstroBin. So I got an email from them asking me if they could post my photo on their Facebook website. So I was very pleased with that. They often look at AstroBin and pick out photos from amateur photographers that they want to post. So I think I'm making progress. So calibration frames, again, we're talking about the good, the bad, and the ugly. And the whole purpose of calibration frames is to take all that in our light frame, the good, the bad, and the ugly, get rid of the bad, get rid of the ugly, and wind up with a single frame which contains the photons from our signal. So 3 phases again: capture. Here's where we spend all of our time getting our data. And once we get our data, we need to process it in a way that we can actually use it and create our photographs. And calibration is that key point of linking our capture to the creation of our image file. This is my first Astrophoto. And if you can recognize it, it's supposed to be M42. Horribly out of focus. You can actually see some color, but when I first got this, I was amazed. This got me hooked. And after a year's worth of working with it, these are the kind of things I was able to create. This is now the picture of M41. One I'm really proud of. Lots of nebulosity, definition in the core. This is actually a combination of exposures at 60 seconds, 30 seconds, and 5 seconds to bring out various aspects of that M42. And these are some other photographs that I've created, none of which would really been capable without having a good calibration process. Certainly much more difficult to be able to get decent looking photographs if you don't have a good calibration process. So really that's kind of the end of this part of the presentation, but really when you're dealing with a hobby that deals with the limitless universe, we're really talking about to infinity and beyond, because the opportunities are limitless. Again, Calibration Files really talks about the good, the bad, and the ugly. And it's a whole process of getting rid of the bad and the ugly and getting us to a point where we only have the good photons of our target left that we can go process. So astrophotography is certainly a journey. It's not a sprint. And calibration frames are really a process that makes it so much easier to get that photograph you're looking for. So that's a kind of a quick synopsis of what I learned about calibration frames. Later on in the year, I hope to be able to present a little more detailed information on my whole process as a newbie trying to get involved in astrophotography, and tips and tricks and lessons I've learned and mistakes I've made and things I would change if I would start all over again. So with that, that concludes it, Gordon.
All right, thank you. Thank you, Sid. A great presentation about how amazing our hobby is, astronomy is. I mean, you can get as deep as you want into anything. Astrophotography, you can just use a DSLR attached to your telescope. The next step appears to be complicated. However, it's a process. And once you get the process down, then you just continue on through and you get those fantastic photos, those images that like Tom Mozdzen puts out. And I noticed Steve Rutenberg is with us, and those that he puts on Facebook. So again, it's a process. You have to learn it. Sid is also the president of East Valley Aviators, which is the radio-controlled airplane club. So he's got 2 hobbies going on, and he can manage to do very well in learning some very detailed astrophotography. So he should be a good motivation for anyone who wants to start on their own. So I will hand it on over to Tom. Thank you, Sid. Okay, Tom, if you want to introduce our main.
Okay, I'll introduce Felipe. My path to Felipe started with a chat with Tom Mozdzen saying, let's see, I've got June, July, and August I need speakers for. What do you think? And Tom said, I met Felipe in Chile a while back. He'd make a great speaker. I'm like, okay, let's do it. Let's go. Let's get Felipe here. It's easier to do it over Zoom when you're in a sort of COVID restrictions than to try and arrange an airplane flight to do it in person. So what a better time. So so Felipe is a science operation observing specialist at ESO at APEX, and ESO is European Southern Observatory, and APEX is the Atacama Pathfinder experiment, one of the highest observatory sites on Earth at an elevation of 5,100 meters, which I think is about 17,000 feet. It's a 12-meter diameter telescope operating in millimeter and sub-millimeter wavelengths, infrared and radio wave regime. So that sounds like an awesome job. Felipe says he likes to think of himself as an amateur astronomer, even though he's getting paid to do really sophisticated professional work. It's best to keep the spirit of amateurism in the back of your mind. I think you have more fun that way, more flexibility. Let's see. So you've been working on various telescopes for what, the last 30, 40 years. So I'm just really anxious to hear about the history of radio astronomy in Chile. It's a hotbed. You know, everybody wants to build there because of the great sites it has. So I'll stop talking and let Felipe take over and tell us all about the observatories.
Well, thank you very much, Tom, for the presentation. It's my pleasure and my honor to be here with all of you, and I hope that we're going to enjoy a great time talking about what the topic that's been part of my life. So to get started, I will share my screen, and I'll go for it. And then if I play this, you can confirm, please, can you confirm that you are actually seeing my screen? Is it okay?
Looks great, yes.
Okay, thank you. So, well, now with the screen presentation, we can move forward the main topic. So, first of all, again, thank you very much for the invitation. I think that I'm gonna enjoy quite a lot this moment, because every time I get an invitation to talk about something that I like, I feel like an honor, and I think that it's such a privilege to share this with you guys. So I'm going to talk about the history and highlights of radio astronomy in Chile. My name is Felipe MacAuliffe, and I'm an amateur astronomer. I work as an observing specialist at the European Southern Observatory. And when it comes the moment to talk about radio astronomy, and specifically in Chile, we have to define a few things about what radio astronomy is about. So when you look at the starry night, and when you look at the galactic center, as you see in this picture now, you see the galactic center, you see the molecular clouds, you see the stars all around. It's absolutely mind-blowing. As a matter of fact, a couple of nights ago, I was observing with my set of optical telescopes, and I had the amazing privilege to see the Milky Way transiting at the zenith, which is amazing. And then you realize, well, is that all just visible light? And then I say to myself, come on, I mean, what else would you expect out of this beauty? I mean, there's absolutely nothing else to add. But if we think in terms of electromagnetic radiation, there's actually a lot more than just light. And that is distributed over a range in the electromagnetic spectrum, where what we really get to see in the universe using our own eyes is just the visible light. And the familiar image of the Milky Way and the light and everything. But that is, as you know, a very tiny portion of the energy that's been emitted in the universe. So if we go to the increasing energy side, you see here the wavelength that gets actually shorter and shorter, and the energy gets higher and higher. Then you go into the gamma rays, or you go into the X-rays, and even to the ultraviolet. And then if you move away to the increasing wavelength with less energy photons, then you go into the infrared region of the electromagnetic spectrum, and then into the amazing radio waves. Why amazing radio waves? Because this is the topic of this talk. I'm not saying that infrared or gamma rays or X-rays are not amazing, but from my side, and I've been in astronomy for so many years, and I've been focused on radio astronomy all of my life, I still think that it's kind of the best place to be, even on top of the optical astronomy, and you will see why later on. Anyway, if we just look at the Milky Way, this is the galactic plane in the optical window, as we are all familiar with, but then we can observe the same object using different kind of instrumentation that basically detects different nature of phenomena in the universe. For example, if you look at the galactic plane, you see several dark spots, molecular clouds that are actually not emitting any kind of light, and even worse, they are actually blocking the light from behind the cloud. So basically, in the optical, if you want to see what's inside these dark patches, you see basically nothing. So then if you move to some other wavelengths, you will unwrap that radiation, a radiation that seems to be completely non-existent, and then it comes into something that is real. By example, if we go to the top, we see the radio waves coming from the radio continuum, all the molecular clouds here. So if you see this map, then you see that a lot of information that seems to be hidden away in this molecular gas is actually popping up, and we see a universe that is unseen by the light. So by taking advantage of these multi-wavelength Milky Way maps, then we have to think on how did it happen? How this all things started. But before we go into the history, we have to review a bit on how a radio telescope works. And it's extremely simple. A radio telescope is very much like an optical telescope, but we are observing radio waves. We still make use of a primary mirror, or a primary reflector, as we call it. It's usually much larger than an optical mirror because it's easier to build. And since we are observing longer wavelengths, we really don't care about the precision of the shape because we're observing longer wavelengths. And then basically, by concentrating the incoming radio waves by using the primary reflector, then the concentrated signal bounce back into the secondary reflector, and then, depending on the design, in this case it's a classical parabolic radio telescope, then the signal goes concentrated through the hole in the mirror, like a Cassegrain telescope, and then it goes into the receiver cabin. And in the receiver cabin, then we have all kinds of instruments, receiver, amplifiers, and then the signal goes into some kind of a computer that records everything. We call it a backend. And then we simply go and display and analyze the object that we are pointing at. So in this case, if we look at the image of Messier 42, the Orion Nebula, in our terms is the more Orion molecular cloud complex, then if you look in the very inner region, then we see this image of the M42, and then we can actually obtain spectra of different molecules inside the core of the Orion molecular cloud. And what we see here at the end of the day, it's just a spectrum where you have a velocity and antenna temperature or intensity. So in this case, velocity is basically wavelength, it's basically the same. So you can think of wavelength or frequency or radial velocity, where you see the positive velocities, which is basically a redshift. If it goes positive, it's a redshift, so the gas is going away. And if it's blue shift or negative velocity, it's a blue shift and the gas is moving towards us. So it looks actually quite spectacular and quite simple, but how this whole thing got started? And it got started actually quite some time ago, but not long ago. It's actually less than a century of history of radio astronomy. Well, back in 1929, the research division of AT&T and the Bell Labs, they were looking for ways in order to make telephone calls across the Atlantic. And they were developing a lot of technology in order to achieve the goal of having good communication between Europe and the United States. But there was a problem, well, actually several problems, but one of the most annoying problems was sources of unknown noise, static noise that showed up in the transmission. So they were testing everything as a lot of noise, and then it dismissed, and then back again, and then it dismissed. And it was extremely unknown origin. So there was a very young engineer called Karl Jansky, and they asked him, please, we have this problem, we have this noise, we have absolutely no idea from where this noise came from. So please do something, investigate, and came back to us with an answer. So Jansky, what he did, he built a directional antenna operating at 20.5 megahertz. And actually, this antenna was it was very funny antenna. It was called the Jansky merry-go-round telescope. And it was actually this set of very interesting antennas mounted in this system that you could actually rotate the whole thing in azimuth, like a radar, think that way, in order to point and try to identify the source of the noise. And actually, after 4 or 5 years of research, he ended up with a conclusion. He concluded that the noise, or the unknown noise, was basically being originated from the galactic center. So this hiss was coming actually from the outer space. At the beginning, it was thought that this was actually originated in the sun, but that was wrong. And then he realized that this noise was coming and going in once per day, he was coming and going, and then he realized that it actually was coming and going every 23 hours and 56 minutes, which is the sidereal day. So there he narrowed the search to the galactic center. And actually this discovery was widely publicized at the New York Times, and it was actually at the trending topic, if we call it in the nowadays definitions. The downside of this history, well, after the mystery was solved by Jansky, basically the Bell Lab didn't show much interest on carry on with the research and everything, because it was clear it was this radiation coming from the galactic center, and it was like, okay, there's nothing to do about it. Fortunately, there was a student, well, not a student actually, a young radio engineer in Chicago, that got very interested on the findings of Karl Jansky, and in 1937, he decided to carry on with the Jansky's findings. And he was such a skilled guy, and he decided to build in his own place a radio telescope of 9.5 meters in diameter. And then he actually became the very first radio astronomer in history. Jansky was kind of detecting the source of noise, but he was not really researching on the origin of this. But then Grote Reber, he got into astronomy, and he got into the serious topic, and he actually managed to identify not only the galactic center, he also identified sources of noise coming from Cassiopeia or from Cygnus. So he was actually a real radio astronomy, and what you see here actually are the maps produced by him. And in 1944, the first radio map of the Milky Way was produced by him. Later on, in 1951, another team of astronomers detected by first time the atomic hydrogen. And this idea of detecting molecules in the interstellar space became real. And then it was just like a first ignition that got extremely enthusiastic all around the world to build radio telescopes and do serious research to identify molecules all around the universe. And actually, back in 1968, there was a first detection of water and ammonia in the interstellar medium. So then we were talking about very interesting molecules being detected through the radio waves. So up to this point, radio astronomy, it was kind of going through the first steps and showing up very interesting results to the scientific community. So in 1970, the carbon monoxide was actually first detected in space. And what is so important about the carbon monoxide? Well, as we all know, the hydrogen is the simplest and the most abundant element on the universe. And of course, the molecular hydrogen is also the most abundant molecule in the universe. But unfortunately, in typical conditions, the H2 does not emit any radio waves. So if you want to detect this hydrogen, you have to go around and look for a kind of tracer. So the CO, or the carbon monoxide, actually acts as a tracer in order to detect the invisible H2, which is, again, the most common molecule in the universe. So taking advantage on this discovery, there was a team of astronomers going all around in the quest of mapping extended molecular clouds. Molecular clouds are those dark clouds that we get to see in the Milky Way, those dark patches. In the southern hemisphere, there's this famous coal sack that we will talk later on during this talk. What you see is just darkness against the bright background of the Milky Way. And those molecular clouds are actually very rich in all kinds of molecules. So then in 1970, Paz Thaddeus et al., he started a CO survey using a 5-meter dish at the McDonald Observatory in the north. And he was basically following the path of the carbon monoxide on the Orion molecular cloud complex. Unfortunately, that telescope was too large. I mean, if you are mapping with a high magnification telescope, it will take forever to reach the boundaries of your cloud. So then this idea of building a smaller telescope, what it was called a mini telescope, came into the stage. Rather than having a 5-meter dish, let's work with a small one. Actually, it was a 1.2-meter dish to do fast mapping. And this little dish that is shown here is actually a 1.2-meter dish inside a dome. You see it here, picture from outside. And if you're familiar, of course, with Manhattan, you will recognize the Empire State Building in the background. So doing millimetric radio astronomy from Manhattan, maybe you were not aware of this. So this small radio telescope, the northern version, was observing the CO 120 at 115 gigahertz, which basically correspond to 3 millimeters wavelength band from Manhattan, New York. And this amazing mini telescope started the quest to map the Milky Way in molecular clouds. But meanwhile in Chile, because we've been talking about everything in the northern hemisphere, but what happened in Chile meanwhile? Well, in Chile, we had the Cerro Tololo Inter-American Observatory. It's the southern brother of the Kitt Peak National Observatory in Arizona. We had La Silla Observatory with amazing amount of telescopes, all of them optical. Right in the middle, the National Astronomical Observatory in Santiago de Chile. Las Campanas Observatory, which is an optical observatory in the north of Chile, managed by the Carnegie Institution of Washington. And also, this is actually quite interesting. The very first observatory in Chile was the Cerro Manuel Foster Observatory, which hosted a 94 centimeters optical telescope, which was the former largest optical telescope in the southern hemisphere. And believe me or not, this telescope is located in the middle of Santiago de Chile city, one of the most light polluted cities ever nowadays. But back in the previous century, when this observatory was set, it was one of the best places of the world for astronomical observations. So anyway, moving forward, I'm coming back to the ray astronomy topic. Back in 1959, the professor Federico Rutland asked Jorge May the installation of a new facility. He wanted to have a radio telescope in Chile. There was this development in the Northern Hemisphere about ray astronomy, and he was actually very smart on thinking, hey, we have to do something here in Chile. We have professional astronomers like La Silla, Tololo, Las Campanas, blah, blah, blah. And what about the radio waves? So then Jorge May found a really nice place in the south of Santiago called Rinconada de Maipú. There was this radio observatory that made observations on Jupiter in collaboration with the Florida University. Actually, it was the very first BLBI, so very long baseline interferometry baseline between Maipú and Kentucky, more than 7,000 kilometers away. And it was using antennas of 512 dipoles at 45 megahertz. So the very first map of the southern sky was actually observed from Chile, from Maipú, in the south of Santiago. It was actually shut down in 2001, and I had the privilege of visiting the facilities of that observatory was still active, and it was actually a very interesting control room. I still hold memories of those wonderful days. Anyway, it was the time to open the millimetric window in the southern hemisphere. So again, Jorge May led the installation of the first millimetric radio telescope in Chile. And in 1980, the southern version of the mini telescope that was located in New York City, it was installed down in the Cerro Tololo Observatory. The same, exactly the same optical design, the southern brother of the telescope in the north was installed in the Cerro Tololo Observatory. And here you see the dome at the Cerro Tololo Observatory, and you see the small dish facing towards the camera. And it was actually very interesting because by first time it was possible to have a pair of radio telescopes operating at the same wavelengths, one observing from the north and the other one observing from the south. And it was possible combining the data to produce a large survey of the sky in the carbon monoxide molecules. So out of this telescope, there were a lot of interesting surveys, being the most important one, the Super Beam, which basically combined data between New York City and Chile. And then the Galactic Center survey our Corona Australis, the Aquila, blah, blah, blah. And then we can go through many, many different products that were obtained using this set of telescopes. Some of them in New York City, then another one in CFA, because this one was later moved to CFA. And you see this amazing collaboration of telescopes between United States and Chile. I had the privilege to work in some of these observations. Actually, it took my role when mapping the third quadrant of the Milky Way, and then part of the cold sack as well. So we were talking about the cold sack. This is how it looks. Maybe most of you have already been in the Southern Hemisphere. If you have never been in the Southern Hemisphere, you are very welcome to come here and enjoy the southern skies with the Southern Cross high in the sky. And what you see is alpha, beta, and then you see here this amazing dark nebula, this huge molecular cloud that, again, if you observe it through the optical window, basically you get nothing. So if you apply for observing time in an optical telescope to observe the cold sack, your project will be rejected by the committee. But then if you apply for observing time in a radio telescope, what you get to see is this kind of maps where you see the abundance of the, in this case, carbon monoxide in the cold sack. What is actually quite interesting, you can actually look through these absorption clouds. So you can get to see what's behind the cloud and what's being emitted in the cloud in the radio waves. So you can either see the distribution in longitude and latitude. I'm talking about galactic, of course, galactic longitude, galactic latitude, and the color scale denotes the abundance. Or you can visualize the same data set, but looking at the galactic longitude and then making a cut in radial velocity, so you can get to see the cinematics or the kinematics of the gases. So which ones are going away, which ones are coming towards us. So you can get to see a lot of interesting astrophysical phenomena by observing this kind of maps in the radio window. So a lot of interesting papers were produced by this small telescope, led by Tom Dame, Cohen, Jorge May, of course, Lasho Genima, who later on became the science operations leader of the Atacama Large Millimeter Array. So a lot of scientists coming to work in Chile produced a lot of amazing data out of this telescope, combining data from the north and from the south. So now we can actually share with you a beautiful map of the galactic plane by combining data from the north and from the south. And then you see the galactic center in molecular clouds. And you can see the abundance of all the elements that's being mapped. And then you can see the longitude velocity map, where you see basically the rotation of the galaxy. Some of the molecules are moving like that way, and some are moving this way. So then you can really see the rotation of our galaxy. In the optical, this is extremely difficult because the line of sight is absolutely blocked by the molecular clouds. But in radio waves, you can really get to see the rotation of our galaxy. So actually, back in 1997, in the 30th of April, this image made it to the Astronomy Picture of the Day. Now we are all familiar with this amazing website, and every day, actually my screensaver in my computer is Astronomy Picture of the Day. But if you think back in 1997, the first time there was a radio map in the millimetric waves of the Milky Way in molecular maps. So it was actually a kind of a highlight of the history in radio astronomy, that one day in 1997, the image made it to the Astronomy Picture of the Day. Anyway, but that time I got involved in radio astronomy. Actually, you can see an image of the small radio telescope with the young Felipe MacAuliffe, looking much younger. I was actually 20 years old. There's a small reference here to an album of Pink Floyd. This is actually the cover of the Division Bell, and the first song is called Cluster One. And why I citate this amazing band, because by the time I was observing with this small telescope, this album was released. And it was such an amazing moment in my life that my working place was actually featured on an album of Pink Floyd. And this was one of the papers that I had the privilege to be on the list. Again, I'm not an astronomer, I'm an amateur astronomer. And I've been dreaming with this all my life. And my very first time in my life, I was getting paid to do what I love in life. And then I ended up in a publication observing something which was extremely interesting and going along with the music of Pink Floyd. Life was good and it's still good. Anyway, let's move forward. So after the success of the small radio telescope at the Cerro Tolol Observatory, there was a lot of room for improvement and for larger telescopes. And the European community decided to install in 1986 the Swedish ISO 7mm telescope. And now we're talking about a huge telescope. It was actually a 15 meters in diameter, which was by many years the largest submillimetric facility in the Southern Hemisphere. This radio telescope was installed at La Silla Observatory, and it was operated by the ESO, by the European Southern Observatory, and the Onsala Space Observatory. And this telescope featured spectral line receivers and bolometers. But the problem The site at La Silla Observatory was barely sub-millimeter conditions, with a lot of content of water vapor. We'll talk about that later on. But it was a good site, but was not the perfect site. Why I mention this right now? Because it will make sense later on during the talk, why we are still looking for better places. But anyway, this radio telescope settled down as a pathfinder of future projects as APEX and ALMA. And I had the privilege to be part of the science operations group of the CEST for about 8 years of my life. And I actually did the very last light of the telescope in 2003. By the way, most of you might imagine how sad is the moment when you close down a telescope. After all of the years observing the sky and suddenly you park the antenna or you park the telescope, you put the covers on and this is it and you say goodbye. It's actually like killing someone. Well, I never kill anyone in my life and I will never do it. But the closest I feel to that is when you do the very last light of a telescope. It's such a sad moment. Anyway, let's review some of the highlights of the CEST. The CEST did amazing observations around the Centaurus A galaxy, which is a very massive, active nuclear galaxy in the southern hemisphere. There is actually a black hole that is ejecting bipolar fluxes. And it was possible to map those bipolar flow using the CEST radio telescope. And what you see here in the year 2000, it was this amazing map of the unusual galaxy Centaurus A. Then, back in 1998, we had an amazing visitor. It was the Hale-Bopp comet, one of the most massive comets we ever had in our lives. Some fundamental molecules were discovered by this telescope, especially methanol and hydrogen cyanide detected at record distance. So it was another scientific highlight of the CEST. Actually, I'm going to show you a really nice map that I truly like. First, this map shows a map where the x-axis is distance. So the left side is a comet approaching the sun, and then the right side is the comet going away from the sun. So as the comet gets closer to the sun, the production rates of molecules increases because of the sublimation of the material and the gases getting excited by the proximity of the sun. So the abundance and the production rates of all the molecules increases. And then as soon as the comet goes away from the sun, then the abundance decreases. So we used to call this the Christmas tree of the Hale-Bopp comet. And it was such an interesting experiment. A very interesting instrument installed at the CEST was the SIMBA receiver. SIMBA is basically a bolometer, and a bolometer, in very simple terms, is a thermometer. So you can measure directly temperatures in the universe by coupling this receiver into the telescope. So you can measure and you can actually map very extended regions of the very cold gas in the universe. It was the very first bolometer camera ever installed in the southern hemisphere. Well, no, I don't think in the southern hemisphere. I think that the Australians were first, but this one was extremely successful. Anyway, I hope that there's no Australians around, otherwise they will hate me. But SIMBA was extremely successful. Then another countries were actually looking into how we get into the game. Everybody seems to be gathering around Chile, United States, Europe. Well, then Japan got into the game. And then back in 1997, they installed behind the CEST control building the very small telescope 2. It was a 60 centimeter dish, and they wanted to combine data from the Cerro Tololo telescope, that was 1.2 meter, together with the data from this BST2 in order to get CO1 to 0 and CO2 to 1. at the same resolution. And it was a pathfinder for the Nanten and Nanten 2 telescopes. So Japan was in the game and producing wonderful data. But then, all of these places, Cerro Tololo, Las Campanas, La Silla, they were good observing sites, but they were not the best sites. They were better sites. And there was a campaign, a site testing campaign, going very intense in the north of Chile. And in the north of Chile, in the second region, there's a village called San Pedro de Atacama, which is a very famous destination for people coming to Chile. And just by chance, nearby San Pedro de Atacama, there is a place called the Chagnactor Plateau, which is right in the border of Argentina, Bolivia, and Chile. And this site is actually at 5,000 meters above the sea level. The higher you get, the better it gets. Why? Our worst enemy in observational astronomy is this thin layer of atmosphere. Without it, we all die, so we need it. But for astronomy, we want to get rid of the atmosphere. Hopefully, we can actually dry it away, but we can't, otherwise we all die. So we go higher and higher and higher in order to get the minimum layer of water vapor and atmosphere in between the telescope and the source. And you measure this by looking at the transmission. And the transmission in this plot, you see the frequency in gigahertz against the transmission, being number one, 100% transmission, and being zero, completely blind. So nothing being emitted arrives to the telescope. So the transmission depends on the content of water vapor, actually the precipitable water vapor content. Think on this way, you have a lot of water vapor and then you compress a column of the atmosphere and then you compress it and then you measure it in millimeters. What we want to have is the least amount of water vapor in this measurement. So the lower the water vapor, the higher the transmission is. So that's why you see three colors here. And you see that the lower water vapor, the red, the transmission gets higher. The higher the water vapor, the transmission gets lower. So we need to look for very dry places. And Chagnactor Plateau is the place to go and install new radio telescopes. So most of the time, the water vapor at the Chagnactor Plateau is below 1 millimeter. So that's why we call it a submillimetric place, which was barely the case for La Silla Observatory with the CEST. Then 25% of the times, the water vapor is even less than half a millimeter. So it's basically nothing. I always insist on the point. It's like putting a telescope on the space, but at the ground level, at the very high ground level, but still at the ground, with the cost of operation to be at the ground level. So also something that is very interesting is the outstanding phase stability found at Chagnactor. What is phase stability? Is how stable are the conditions over the course of 24 hours. It's like this astronomical seeing. You want to have good seeing in optical astronomy, but if the seeing is jumping from very good to good to very good to very bad to good to very good, it's useless. You want to have it as flat as possible. Otherwise, you have to calibrate a lot, or you have to refocus. You have to face all kind of problems with calibrations. So the only problem of the Chagnactor Plateau, the water vapor gets extremely bad during the Chilean summertime, or as we call the invierno altiplánico. The water vapor goes very high. So in between January until March, we basically close the operations of some of the telescopes at the Chagnactor Plateau because the water vapor goes way too high. But then we get the price back for 10 months a year with amazing low water vapor. So the Llano de Chagnactor, by the way, Chagnactor means takeoff place, the place where you take off. And it's actually quite symbolic because humankind partners all around the globe, ISO, Japan, United States, they all look at the same place, the China Top Plateau, to settle down a unique project. So before settling down a unique project, there were some interesting projects installed at the China Plateau. First, it was the Cosmic Background Imager, the CBI. And it was basically designed to study the cosmic background, which is basically the early universe. It was a partnership between a lot of institutes, a lot of universities, and it had the first light in the year 2002 and produces one of the most amazing maps of the cosmic background, very early universe. Then the Japanese, they decided to install the Nanten sub-millimeter observatory, originally located at Las Campanas. Actually, this is the same radio telescope obtained at Las Campanas, and then it was moved Nanten and then Nanten 2. It was located at Pampa La Bola, and a partnership of all kind of universities from Japan, of course, and of course the Universidad de Chile. Then another huge telescope, 10 meters diameter, the Atacama sub-millimeter telescope experiment, and another partnership of several institutes, all of them in Pampa La Bola. And then in 2003, a real pathfinder for the ALMA landed at Chang'e, a partnership between the Max Planck Institute for Radio Astronomy, European Southern Observatory, and the Onsala Space Observatory. The APEX project, okay, this is the China Top Plateau, and this is the location of the APEX telescope, and this is the location of the Atacama Large Millimeter Array. And this plateau here, again, is at 5,000 meters above the sea level. Very, very high, beautiful place in every sense. Lack of oxygen, not easy to walk up there, but still nice. A brief history of APEX. As I say, APEX is a partnership between the Max Planck, ISO, and the Onsala Space Observatory. And what is actually very important, every time a telescope is installed in Chile, Chile gets a grant of 10% of the observing time. In 2002, there was a first agreement to operate APEX. That's a picture of the inauguration. And then it was basically inaugurated in September 25th, 2005. It was a grand opening. This picture shows all the participants of the grand opening. I'm up here, actually. And we are operating this telescope in 24 hours mode. Before the pandemic, it was like that. After the pandemic, minimum operation survival mode. And now we are back in 16 hours mode. And I hope that as soon as the pandemic is over, we will go back to 24 hours on sky. The telescope will run until 2022. I mean, at least that's a current agreement. Then we'll see what happens afterwards. I hope that we will have APEX for a lot more years. This is the APEX antenna. So basically, it's a 12 meters telescope where you have a Cassegrain cabin with the optical mirror. So basically, the first mirror is the M1, the secondary unit is M2, and then in the Cassegrain cabin, there's an M3 mirror that basically sends the incoming radiation into receivers inside the Cassegrain cabin. Otherwise, we have extra cabins called Nasmith cabins, the Nasmith A and the Nasmith B. So what's the advantage of all of this? It's a very versatile telescope. We can have several instruments all around the A, B, or C cabin. So it's a very versatile instrument. Actually, this telescope is a modified prototype of the ALMA vertex antenna, and it moves extremely fast. Actually, it's used 6 degrees per second. It's actually quite interesting. It's a very fast antenna. I remember when I saw it my first time moving, it was unbelievable. So we have a control room with a control system that can be opened quite easily from anywhere in the world. Actually, I can grab my iPhone, I can open the control system and, well, not observe from my iPhone, of course, but I can actually get connected from any place of the world to the control system. I was talking about the bunch of instruments that you can install. This is an outdated list of instruments because now we have more instruments. Some of them have been already decommissioned. And here you see the distribution of different instrumentations along the frequency. So we can basically cover with all of the instruments the most interesting windows that makes it to the ground. Obviously, in this region, we don't have anything because the atmosphere is completely opaque. So we have to go in space to detect this. What kind of size categories a telescope like APEX does? Well, most of the time we do interstellar medium. So basically Milky Way, molecular gas, star forming regions in our Milky Way. Then a lot of science around stars, also in the Milky Way. But actually a large portion is also devoted to extragalactic or high redshift universe. So again, it's not only versatile in terms of instruments and also in terms of size categories. A few examples, you can map your favorite objects. Again, we see Centaurus A, but this time, rather than that former map with contours, low resolution contours that was very exciting by the time, but now the same thing observed with a large bolometer camera, with a bolometer called La Boca, large bolometer camera, and you see, and you get to see this massive galaxy ejecting this bipolar flow, ejected by the black hole. So it's actually very interesting to see this map. Also, large surveys, Atlas Gal, it actually is it's a legacy product of the Atacama Pathfinder experiment, where you can map the clouds, the cold clouds in the galactic plane. I'm showing now a real data set composed by La Boca data. Also, we have data from the Planck satellite, and also we have Spitzer data, all of the data in the same animation. So using this set of cameras and this set of data, you can really dig into the molecular clouds, and you can really get to see what's in the galactic plane, what's actually in the galactic center. Then this telescope also observe deep surveys. This is the result of 280 hours of sky in a little portion of the sky called the extended Chandra Deep Field South. Basically, the same thing as the Hubble Deep Field, but in this case in radio. There was this empty sky, and after 280 hours on sky, in this tiny portion of sky, a lot of sub-milliometric galaxies were discovered. So there's no empty in the universe, most likely. I mean, anywhere you point your antenna, your telescope, whatever, there's something to observe. So it's countless hours, days, and months of entertaining, call it like that. Astrochemistry, what is interesting, this is the complex of Rho Ophiuchus in Ophiuchus and near Antares as well. You see Messier 4 here. There was a very interesting discovery. Basically, it was hydrogen peroxide, which is basically H2O2. We're talking about an interesting molecule that tells us a lot about how the life might form in the universe by studying the initial elements on the life forming. And of course, you can observe high Z sub-milliometric galaxies and how you can observe actually stuff forming in the early universe. All of this observed with APEX. I'm using APEX as an example. I could use other telescopes also. But since I work at APEX, I mean, I worked since the very beginning. I'm a kind of fan of this telescope, but there's also a lot of amazing science produced, of course, by other telescopes at the China Plateau. But just one telescope, it's not enough. Radio waves The only problem is that is the low resolution. So if you want to go for high resolution, a larger dish is needed. So rather than going from 12 meters, you would like to go to 50 meters, to 100 meters, to 1 kilometer or whatever, but then there's absolutely no way to build a monolithic dish. So then you have to combine several smaller telescopes into an interferometric telescope. And of course, the Europeans, the Americans, and the Japanese were looking for this Changnato Plateau, and they were all looking to create huge radio telescopes around the area. So unity is a strength, and they were all looking for a large project. And that's how ALMA, or the Atacama Large Millimeter Array, came into place. This was the very first image of the ALMA telescope, the antenna galaxy, with just few antennas. Then, in 2014, the very final antenna arrived to the plateau. And then the real science started with the array at the full resolution. What you can get to see with ALMA is absolutely mind-blowing, because the baselines of the ALMA can go up to 16 kilometers. So it's like having a single radio telescope of 16 kilometers in diameter by arranging a total of 66 antennas, all of them pointing to the sky. So you can go into very high detail observing images of star forming in the very distant universe. Some kind of things that are extremely difficult to observe because of the spatial resolution. But now, by using ALMA, it was possible to even resolve H2 regions in the very first stages of star formations in the distant universe. And I can go talking about highlights of ALMA, but then it will be just like analyzing all the career of Roger Federer. And every time he wins something, it's like, okay, he did it again, he did it again, he did it again, and it's endlessly. So if you are into the tennis world, you will see what I mean. It's like analyzing how amazing is Roger Federer. If we want to go into every aspect of ALMA, it will be the topic for another talk, maybe in the future. So I would like to show you a bit the collaboration between different projects. By example, you can combine data of ALMA and APEX and how it was possible to discover massive conglomerations of forming galaxies in the early universe. In other words, how the galaxy clusters get formed at the very early stage. We are not talking about the star formation. We are not talking about how the galaxies get formed. We are talking about how the clusters of galaxies, they all get together. And this is a really good example of a wonderful collaboration. This is a small telescope called the South Pole Telescope that detected a candidate that then was observed by APEX, and APEX basically showed a kind of a structure, but then it was still unresolved. But then ALMA resolved this stage of a cluster of galaxies being formed. So this is why we have to work all together in order to increase the resolution. Also, you can combine data between ground-based telescopes like APEX or ALMA, and you can also use data from SOFIA, which is the Stratospheric Observatory for Infrared Astronomy. Basically, the radio telescope goes into a modified Boeing 747 SP and goes way above the level of the atmosphere in order to increase the transmission that is actually absorbed by the clouds of water vapor. So then you can combine data in order to get this amazing set of data of NDC 2023. But we always want more and more and more. And I think that this is the global partnership at the largest possible scale we can think of. the Event Horizon Telescope. What's the idea behind this? Maybe you're all familiar with this. The idea was to image the event horizon of the massive black hole in our Milky Way, the famous Sagittarius A star. But one telescope is not enough. Even ALMA, with all of the resolving power, forget it, there's no way. You have to combine data from several telescopes all around the globe in order to create a virtual telescope, Earth size. And that's what is the Event Horizon Telescope is about. The idea was to resolve the event horizon of a massive black hole. So by combining baselines of different stations all around the world, ALMA, APEX, LMT, JCMT in Hawaii, IRAM in Spain, and so on, and of course the SPT in the south, combining the power of 8 different observatories in the world, the idea was to move all the telescopes to the target Messier 87, which is a very famous, extremely massive object at 55 million light years away in the Virgo cluster with 1 trillion stars. And inside this active galaxy, there's this jet of ejected material with a huge, very massive black hole. And in the year 2019, in April 10th, it was finally released to the public, the very first image of the event horizon of the black hole. And this iconic image was possible thanks to the collaboration of so many observatories and in Chile, 2 of the participants making a groundbreaking event in the history of astrophysics. What's the future for us? Of course, the future will be to image the event horizon, but in the in the black hole of our own Milky Way. Also, there is a new telescope, the SICAT Prime, that will be an antenna at 18,000 feet above the sea level. And there is a first light probably in 2021 because of the pandemic, nobody knows. And also there's this idea of a 50-meter single dish telescope also in Challenger. I would like to finish this talk by paying tribute to a lot of important people that were crucial in the history of radio astronomy in Chile. Without all of them, this would be possible. So just a second of tribute to all of them. Of course, Jorge May, that was mentioned in this talk at the very beginning. A lot of people that made it, that made the contribution for all of this. So I would like to share my last image. That's my email address if you want to contact me. And on behalf of the Apex Telescope and on behalf of myself, I would like to really thank you for your attention. I hope that I didn't extend this talk too much. The topic is very interesting. And I will open now for questions. So I will stop sharing my screen and I follow your instructions from Phoenix.
Hey, thank you, Felipe. That was really interesting. So much going on there. It's really exciting. Let's see. One of the questions we have, okay, when a new optical telescope starts observing, they call it first light. What is there a term when a new radioscope starts observing?
Well, that's a good question. Actually, radio waves are a kind of light. We are still talking about photons. So we still refer it as the first detection of first light. Actually, for us, even better. Sometimes we refer to first noise. Once you connect an equipment, and then you connect the electronic, and you can get the first readout of the noise, it's actually good because it means that the communication, the data flow, the data system is acquiring. But then, of course, what you want to see is the first real light from the first source. Usually it's a planet, usually it's the moon, usually it's anything bright. It's exactly what we do in optical amateur astronomy. We do align our finder looking at the light of the, I don't know, that is, I don't know, 100 meters away or something, just to focus the finder scope. Once we know the finder scope, then we align it with the primary telescope, and that's the first light for us.
Yeah.
Well, in astronomy, we basically do the same, and we prefer it as first light, even if it's not real light.
That's cool. Let's see. Another question is, well, Jeffrey Sykes asked something in Spanish. I don't know if you see it in the Q&A. I think he's saying greetings from New Mexico. Okay. Let's see. Another question is, let's see, is about, is the current political movement, is there any effect to increase or decrease international cooperation of the observatories, radio, optical? Any comments there?
Well, that's actually quite interesting because we are all affected by pandemic and the economical consequences of the pandemic. So we might have some consequences on the funding for all of these telescopes. I hope not, but I do believe and I do see in real life that the investment in science is not very affected, and so far we are still getting into the stage that we want to go back to real operations. How will be that affected by the contributions of the partners or the international community? Nobody knows. It's a topic that is under development, and there's no final answer to that.
Okay, yeah, good point. Yeah, it's hard to predict. Let's see. Oh yeah, Jeff also asks, what's your favorite Pink Floyd song to play in the background when you're observing? If you have a favorite, maybe several favorites.
Well, anything that is Pink Floyd related goes good first. Now, if you ask me about the best song of Pink Floyd to play while you are observing, I would say that The Dark Side of the Moon goes absolutely perfect. I mean, from beginning to end, The Dark Side of the Moon is amazing. And then if you play Echoes also, it's amazing. But then if you play The Division Bell, which is an album from 1994, it's so science related that it also goes so fine. So the answer is any Pink Floyd song will make it.
Oh, that's cool. Yeah, I've got a nice little USB drive with a lot of Pink Floyd albums. Yeah, it's especially good to turn the lights off and listen to Pink Floyd in the dark. Let's see, another one. Let's see, let me okay, I'll go to Tom Curry. Let's see, do you know of a larger collaboration with telescopes in Russia and China added to the original collaboration? Would they add much more resolution? I'm not sure if he means the Event Horizon telescope. I think he means Event Horizon.
Yeah, but the problem is with China and the East, we cannot do interferometry because they are at the other side of the world, and we have to look at the same object at the same time. And of course, there is a huge collaboration going on in the East. And also, if we think about the square kilometer array, is also another amazing experiment that's taking place nowadays. So yeah, fortunately, collaborations goes far beyond the human imagination, and the boundaries are just set by the size of the universe. So as long as we keep on collaborating globally, we make a better planet.
Yeah, those collaborations are just amazing. Event Horizon Telescope and their plans for the future just get me so excited about the capabilities. Let's see. So Woody Forsyms has a question. What could an amateur do today with a 1.2 meter radio telescope that might be something that the professionals don't have time for, or that might have been overlooked?
Well, low resolution astronomy is still needed. It's not like you do science for years and years with 1.2 meter dish and then this is it. Of course, that you want to go with high resolution and better instruments, but there's still a lot of science to do. Actually, the small 1.2 meter radio telescope that that was installed at Cerro Tololo, sorry, is actually installed at the Cerro Calan Observatory and it's been used as a lab telescope for students. So if you want to have, I don't know, PhD students or students in astronomy, you won't give them an ALMA right away. Or you will give me the Even Horizon Telescope. I don't know. I'm just trying to make a figure. So this small telescope, which are not used anymore in top of the line research, can be still used by not only by students of astronomy. They could be also used by engineers because they have to develop technology for astronomical observatories. So there's a huge application, windows of the application for different brands of people working around astronomical observatories. Now, what if an amateur astronomer would like to build a 1.2 meter radio telescope? It's not easy because you also have to set the instruments, and the instruments are extremely expensive. So doing a millimetric radio astronomy as an amateur level, I don't think that it's possible unless you have a lot of dollars in your pocket.
Yeah. Tom Blake has a question. Tom, you go ahead.
Yeah. Hey, Felipe. We're very familiar, a lot of people in Arizona, with the Very Large Array in New Mexico. It's the next strait over, 6 or 7 hours away. And so I think you said that it goes to an 18 kilometer baseline, the ALMA. And the VLA is even larger, but I know it's at substantially larger wavelengths, longer wavelengths. What'd be like the ratio of the wavelengths that you're operating at millimeter to what the VLA is operating at? Is it 1/10 or 1%, or what's that like?
Well, I don't remember by heart what's the wavelength regime of the VLA, but I do believe they observe in the centimetric window rather than the millimetric window. So we are observing at a different wavelength. So we can basically interact and combine data. But I don't think that they made it to the millimeters. If there's anyone around in the audience that knows that the wavelength of the VLA, I will be very grateful. But the longer you go into wavelength, the less resolution you have.
Right.
So
I'm
if you
thinking
want to go
0.6 centimeters.
Huh?
I think VLAs they're touting 0.6 centimeters, 50 gigahertz.
Yeah, they go to 0.6 centimeters.
Yeah.
6
Yeah, that frequency or that wavelength is so it's so outside my the window I work at. That's
Yeah.
actually it's very low frequency.
Yeah.
In Apex, we observe from the 1.3 millimeter band down to 1.2 terahertz. So basically, that is the regime of the submillimetric telescopes.
Okay. Let's see, another question by John. Could you link a moon radio telescope with an Earth-based radio telescope to increase resolution?
Well, that will be the ultimate baseline. 1 light second baseline.
Yeah.
That would be amazing. The thing is that how will you protect the radio telescope in the moon from the meteorites? I mean, it's still kind of science fiction to me, but maybe there will be some amazing invention in order to avoid falling rocks to destroy the but thinking, you know, in such a long baseline of 1 light second away between the stations in our planet and the moon will be mind-blowing. But I think that there's a lot of technological problems to cope with.
Yeah, it's Yeah, I think that's coming someday. And also linking space-based telescopes with the Event
Right.
Horizon.
Right.
Yeah, let's see. I think that's it. Any further questions, anybody? Oh, I've got one. So your experimental telescope, do you do modifications on that to try out various technologies, or what part of it is the experimental part for the
Well,
APEC?
yeah. Well, I do believe working in astronomy is a never-ending experiment. We
Yeah.
are always going down to the limit. And once you get to the limit, then you have a new limit, a new thing to try. You want better resolution, you want a faster receiver or a faster detector or a truly flat field optic train. And then once you have it, then you have to cope with the atmosphere, and then you develop the adaptive optics and everything. So there's always something to go beyond. In the case of the Atacama Pathfinder experiment, as the name recalls, it's a pathfinder, and it's also an experiment to try out new technology, new receivers. So we have teams all around the world using Apex as a test lab for receivers, and to not only to develop technology on receivers, to develop new science with those receivers that then will be followed by other observatories. So it's a never-ending sequence of teams coming to Apex to install and try out new technology. And that makes it extremely, extremely interesting and fun to work at Apex.
Yeah, so you give them a telescope time to try out their new technology.
Yes, yes.
Yeah. Okay.
We've been using actually receivers that's been prototypes for then receivers on sky on space.
Mm-hmm. All right, sounds good.
Try them out first at the ground level, and then if it works, then to space.
Nice. Okay, well, thank you very much. I think everybody really enjoyed the talk. I know I enjoyed it quite a bit. Gave a little more history than I knew, so I definitely learned a bunch of stuff today. So that was awesome. Thank you.
Well, thank you. It was my pleasure. Thank you for the opportunity, and hugs from Chile to everybody around.
Okay, and I'll hand it over to Gordon. In the chat, you get a lot of kudos. A lot of good job.
Okay, now Felipe, thank you very much. You know, us amateur astronomers, we certainly hear about radio astronomy, but don't get to understand too much about it. So, well, your presentation certainly brought our knowledge up through an interesting presentation. So, thank you, Felipe. That was excellent. Thank you very much. Also like to always thank Tom Mozdzen and Tom Mozdzen for getting such high-level professional type astronomy people to do our main presentations, and Felipe is certainly an example of that. So another example will be Alan Friedman next month, talking about the sun, the solar cycle 25, and how we're getting out of the minimum into the solar maximum. So be sure to come back and join us next month on the 20th of August. So what I'll do here is, let's see, a couple of chats came up. Oh, and just thanking you, Felipe. Yeah, thanks, and fantastic presentation. Oh, yeah. Yeah. So let's see if there's any other questions. Ask them now. And so what I will, since nothing else came in, what I will do is thank everybody for joining us. And I will give the usual countdown and say goodbye to everybody. So 3, 2, 1. Bye, everybody.
Bye-bye.